Arctic boreal forest.
Okay, thank you very much. Good morning, everyone. I'm going to talk a little bit about long-wave emission from trees today. We've had some great talks earlier on short-wave and others, so we're trying to fill in the gaps. It's part of a NERC, which is a United Kingdom Funding Council project, to try and understand a little bit more about energy fluxes under forest canopies and snow-covered areas. I'd like to thank my co-authors here. It's a real cocktail of UK snow science. Slightly distastefully, there's a lot of Rutter in this cocktail, but the bite is provided by Reid. Hancock made lots of work for the data collection. Bob and Brian did a lot of the work, certainly in terms of biological identification, but a nice dash of Essery in there to make it all palatable. So I'm going to talk about hot trees. Before I do this, I'm going to talk about something which is at times a painfully small-scale study. So what are the larger scale implications for this? I think there's three reasons to sort of describe why this is important. At the very largest scale, in terms of land surface modelling, work by Dirksen and Brown showed that the snow-covered extent in the northern hemisphere, the models aren't melting the snow quick enough, particularly in June, July times. Now that's pretty much coincident where there's large amounts of boreal forest in the northern hemisphere, so maybe we're not understanding the energy balance processes at that scale which is causing this delay. SNOMIP2, which was a comparison of forest snow process models, suggested there was quite a large amount of uncertainty in how we constrain parameters and to a certain extent parameter representation in models. So trying to understand more about how we go about representing some of these exchanges could be very fertile ground for model improvement. And finally, of the three, and for those that were John Pomeroy's talk this morning, this is basically sort of taking a bullet for the team, really, and trying to understand a little bit more about the process scale understanding. I won't be the first or last scientist to take a Pomeroy bullet, but I hope I don't bleed out over the next 10 minutes. What I want to do is basically split it into four sections here. So I'm going to talk about a few methods about measuring long wave, and that is really measuring temperature. Measuring the temperature of tree trunks and the air temperature, also understanding more about the canopy structure. We're going to talk about how that tree trunk temperature and air temperature varies, and then how can that be used to calculate long wave enhancement underneath the canopies. What I've put at the top there is a few thermal images of trees in snowy environments. So in Switzerland, in the Arctic, and also in Fraser. So that's Claire Webster, that's Mayer's work, and that's John Pomeroy's 2009 paper. The point of putting it there is these are very alluring images. These are suggesting very strong temperature gradients that are controlled by canopy temperature in snow-covered environments. It starts to suggest if we don't get these right, or we don't at least take them into account, then we're probably not going to estimate through models the right temperatures underneath the canopy. So that's there really just a visual, as a kind of a sort of a justification. Okay, so the study I'm going to talk about, reasonably simplistic. It's one from data collected, the project was in Fennoscandia, so that's northern Sweden and northern Finland. I'm going to talk about the Finnish part of this. So this is a site in Sodankylä, which is in the Arctic area of Finland. It's based at the Finnish Meteorological Institute Research Centre, which is at 67 degrees north, to give you an idea of latitude. So I'm going to show about a month and a half's worth of data, from about the 15th of March to the 25th of April. So we're quite high up, quite low solar angles relatively speaking, but I'm going to contrast to a certain extent two types of forest within this area. So I'm going to talk about what I call the continuous site here, and that's solely got pine trees. The sky view fraction is about 0.29. We've got somewhere quite close by, which I'm calling the mixed forest, and that's mixed as in forest species. So thinking of it's got pine, spruce and birch, which are sort of three large constituents to some of the pan-Arctic plant functional types. So that's got a slightly lower, so a higher sky view fraction, so lower density, as can probably be seen by the photographs there. So I'm going to contrast those and just use some examples in that to illustrate the points or the influence of canopy temperatures. Okay, the sky view fractions were calculated by two methods. The first one was through hemiphotographs, so that's been shown in previous talks, I'm not going to go over it. So you can basically derive, basically from these photographs, a binary representation of what is forest canopy and what is sky. And also what we've done is we've started using terrestrial laser scanning from within the forests. So within plots of 20 by 20 metres, we took enough scans internally in the forest to create synthetic hemiphotographs. So from this, we can basically identify, give or take within the point clouds, the position of the canopy at any point in a 20 by 20 metre grid. And so we can start having quite high resolution maps of what the sky view fraction should be. I'll point you towards Steve Hancock's paper early on this year in Agri-Forest Met if you want further details of that. Okay, I'm going to step through the measurements now that we took, basically of different temperatures, both the atmosphere and the canopy. So, first of all, we have air temperature at 18 metres. So the forest height is roughly about 15 metres in this area. So we're considering that as an above canopy air temperature. We also have temperatures very close to the snow surface, so approximately half a metre. And these were the localities where these 20 by 20 metre plots were. We spent an awful lot of time trying to measure tree trunk temperature. That's not a simple, straightforward thing. There's always problems within that. So what we do, we had two different methods. First of all, this one I've highlighted here is by using thermocouples. So these are by direct measurements. So in essence, putting a little nick with a penknife underneath the bark, or in potentially birch or pine, which is illustrated there, utilizing little gaps there. And we basically fit them in there, fit two thermocouples there, and take an average to try and reduce any spurious measurements. Clearly, that's not exactly skin temperature of the trunk, but it's approximating that, and it's not using any assumptions. We also had measurements using infrared thermocouples. Clearly, at this point, you have to assume an emissivity, and that won't be constant across the bark surface, but it will give you a measurement of skin temperature measurement of the tree. And also, we took some meteorological measurements above the forest canopy, so we know what's coming in above the trees, and some measurements of long wave and short wave below the canopy. So these took quite a lot of babysitting in terms of being leveled and cleaned every day to ensure data quality. Okay, just some data. So this is just the mixed site. So this is the reasonably low density site with both spruce, pine and birch. What we see there, like you see, is that you've got a measurement of thermocouples, that's TC. We have the air temperature at half metre, the infrared thermocouple temperature, and the air temperature at 18 metres in the legend there. Now, clearly you can't see the detail of that. I'll focus in a second. But what I'd like to show there is that you have quite large local synoptic changes in air temperature, in temperatures, where you don't have a large amplitude over a diurnal cycle. Equally, you can have very large temperature changes over diurnal cycles, up to 35 degrees. So this is worth understanding in terms of the energy fluxes potentially going towards the snow surface. So, for clarity, I'm going to try and focus it on 2 days. And that day basically is a sunny day followed by a cloudy day. So the top three plots here, the top one is incoming shortwave radiation above the canopy. So you can see the sunny day followed by the cloud disrupted day. The second one is the diffuse fraction of the shortwave energy that's coming in. That was measured using a BF3. And so again, that just basically again shows the difference between sunny and cloudy. And then the incoming long-wave radiation. So on a sunny day, the incoming long-wave radiation is low. It's basically radiometrically cool, whereas it's radiometrically warm on the cloudy day. So how's this affecting the temperatures within the sub-canopy? So the grey area there is the range of over 64 different points on trees of different species. So what you can see there is a diurnal cycle, but you can also see some of the spikes which are reflecting direct solar heating of the thermocouples in that area of the tree. The blue and the red line are infrared thermocouple temperatures of the skin temperature of the trees, plus the air temperature very close to the snow surface. So what you can see there, particularly at night, is that the air temperature is getting much colder than the temperatures described by the thermocouples. What's quite interesting is the air temperature at 18 metres, which is the magenta line, and that's following more the thermocouple temperatures more closely. So what measurement do we use if we're trying to characterise the thermal regime basically under the canopy? One of the first things that I'll probably worry far too much about is what are the variability in temperatures within a tree. So we're looking here at differences between north and south sides of trees, the continuous site and the mixed site. Just very briefly, the eyes get drawn to some of the larger spikes, some of the large gradients between north and south in the trees. And they can range about 5 to 10 degrees Celsius, so you can get strong temperature gradients outside of a tree. But in reality, when you average that out, the overall mean is about 1 degree C or less. So there's not a lot of north-south bias, despite the fact a lot of energy coming in at the trees. What's possibly more interesting is the difference between the air temperatures above the canopy and sub-canopy. So what you can see in the top plot here is the difference between the 18-meter measurement above the canopy and the temperatures close to the surface. So what we see here is a strong nighttime pattern of temperature inversions. And that's the same, basically, at both of the sites. So it's not necessarily plot dependent. The bottom plot there, you can show that again, shows the inversion strength, really, which is inversely proportional to the temperature. So the very cold nights, you get much colder air under the canopy than you do above it. So possibly that's to do with cool air draining. There's not a lot of localized topography. This is Finland. It's a very flat area. Think like a flat area of Saskatchewan, to give you some credence. So pretty flat. And so there's not a lot of localized pooling in terms of the cold air drainage. It could be much more that there's a lot of turbulent mixing above the canopy. Rather than just the 2 days that I showed before, I'm now going to try and subset to a couple, an average bias at the different sites. I'm just going to highlight a couple of points on this table. So again, just to reiterate, between the north and south of the thermocouples, that overall, there's not a great difference. There is an increase in difference when you subset just the daily temperatures, and you look when there was direct radiation and when there was diffuse. So it's suggesting that although the thermocouples aren't measuring exactly the skin surface temperature of the tree, what they are doing is they are reflecting the incoming shortwave radiation. Also, when we now compare between night and day, we start to highlight here these big differences. So we can numerically quantify the mean bias between the nighttime and daytime temperatures. And the larger numbers there, again, this is all in degrees C, is that you've got large biases up to 4 or 5 degrees at night between what the temperature of the trees are and the air temperature. So it's important to understand which one we're going to use. So when we're going to do this, we use a very simple model here. So we're just basically looking at the energy coming in from the open, so the measured long-wave radiation above the canopy. And then we use the Stefan-Boltzmann equation and a canopy temperature to try and understand what long-wave radiation might be emitted from the canopy itself. So where the canopy temperature is there, we can use any of those measurements that were made to try and understand what's going on. So to try and normalize this, we're talking about enhancement here. So that's really just long wave. Down there is the sub-canopy long wave divided by the long wave coming in above the forest itself. So all I want really to take from the graph at the bottom here is that there's a large enhancement range. So multiples of, between just up to about 1.4 as a multiplier. So key things to look at here is, again, that large diurnal range can be very a point, particularly on cold days, very dramatically cold days, and that signal will be superimposed on the synoptic signal of very cloudy or sunny days. I'll have a diurnal cycle superimposed upon that. Okay, so from the terrestrial laser scanners, what we can do is we can actually get a very high resolution map of sky view fraction. So 10 by 10 centimeter values within the 20 by 20 meter plots. So ignore the speckle in that. That's just a factor of the rotation that we needed to do. But in the mixed site, what I'd just like to show here is that you can see here, this is just sky view fraction changing on a 20 by 20 meter grid. So the cool colors there are basically where the trees are, where there's a much lower sky view fraction. So we can start having an idea of the spatial variability of long wave radiation, at least model estimates within this area. We put out 10 shortwave pyranometers in the area, and the locations are marked there. So there was a structured grid, but when superimposed in the 20 by 20 meter grid, gave a random selection. And also 4 long wave measurements, 3 close to the tree, 1 away from the trees. And how that sits within the whole distribution of sky view fraction is what you can see there in terms of the blue cross there is the position of the long waves. They tend to sit fairly low within sky view fraction. That was intentional to try and understand how much energy was coming from the trees. Can we measure it? And the green circles are more the positions within the distribution of the short wave. Okay, I'm just going to let this loop through. I'm almost finished now. So what we hear is now just sort of an animation on an hourly basis of the sunny day and the cloudy day. What we've used is the sort of the maximum thermocouple temperature to try and run into that very simple model. And what we've done is tried to calculate what the spatial distribution is of long wave energy under forest canopies. So it's going to loop through. So the key thing to look at here is on the left-hand side, we start seeing on the sunny day relative to the cloudy day, we start seeing much larger temperature gradients in terms of what we're modeling. And then on the right-hand side, we show the distribution, so PDFs basically, of what the structure of the energy is. So this gives a couple of things. It starts to show we have can model some very tight gradients in long wave energy underneath forest canopies. And we're also starting to say, well, if we're to only have a couple of measurements of this, how would they be representative of the overall distribution or the chance of long wave? So just to summarize, at high latitudes, even when there are low solar angles and a medium sort of density of canopy coverage, tree trunk temperatures can be substantially larger than the air temperatures, and especially at night. There's a disconnect, again at night, between the air temperatures that are found above the canopy and below, and that will have implications for larger scale modelling. The high resolution measurements allows this understanding of spatial distribution of long wave enhancement at a very high temporal resolution. And finally, the model long wave enhancements, it can be very large, specifically close to the tree trunks. So where this is going, I'll would advert for Claire Webster's poster, which is going to be this afternoon in the session, and she'll basically go on to show how to measure long wave enhancements over short gradients near tree trunks. Thanks for your attention.